Today's session start with some examples of on RE model and introduction to the H parameters. If you consider first example, the transistor amplifier shown in figure uses a silicon transistor with beta equal to 50, VCC 24 volts, RC 5 kilo ohms, R1 100 kilo ohms, R2 10 kilo ohms and RE 470 ohms. Calculate input impedance, output impedance, current gain and voltage gain. For the circuit shown in figure, to determine the voltage gain, current gain or impedance, ZB is depends on that beta times RE, where that RE is not given directly. To determine RE, we need to use a formula from the diode equation that RE is given by 26 into 10 to the power of minus 3 divided by IE, where 26 in 10 to the power of minus 3 is nothing but a voltage equivalent of a temperature at a 27 degree centigrade. We need to determine RE, IE from this circuit and then we need to determine RE. For this circuit, to determine RE, you have to find DC analysis. Perform the DC analysis to determine the IE value. For the given circuit, the circuit is given by R1, R2, RE, VCC. This is R1, R2, RC, RE. This is ground. For this, we need to find, we use a voltage divider network. We need to find an equivalent circuit where this is given by RB is the equivalent circuit, and then this is the transistor, and then the voltage applied is VCC, current is IC. Current, then this voltage is a drive, that emitter base junction is driven by an voltage that is equal to VB. This current flowing through this is IB, and then current flowing through this IE, and then voltage drop across is given by VB plus minus. To determining a emitter current, applying KVL to this circuit, and then you have to determine the value of that base current IB, where that RB is given by R1 is in parallel with R2. This is equal to R1 R2 divided by R1 plus R2. This is equal to 10 into 100 divided by 10 into 10 plus 100 into 10 to the power of 3. This value is approximately equal to 9.091 kilo ohms. And similarly, that VB is given by voltage drop across R2, because this is the denoted with voltage drop across R2. It is given by VCC R2 divided by R1 plus R2. This is equal to, that powers are cancels, then you are going to get VCC is given as 24 into R2 is 10K divided by 10 plus 100. This is equal to 24 into 10 divided by 11. This value is approximately equal to 2.18 volts. Once you have to find the value of VB and RB, we need to determine applying KVL to this path. When you are applying KVL to that base emitter junction, that VB minus IB RB minus VBE minus IE RE equal to 0. For this case, where the given transistor is a silicon transistor, we need to use that VB is equal to 0.7, then IB RB plus 1 plus, we know that already, IE is equal to 1 plus beta times IB, RE equal to VCC VB minus VB. We are going to get this value, IB equal to 24 minus 2.18 minus 0.7 divided by RB is 9091 plus 1 plus beta is 51, beta is given as 50 into RE is 470. This value is equal to 1.48 divided by, this is equal to 33 061. this value is approximately, IB value is approximately equal to 44.77 microamperes. Once we find the value of IB, we need to calculate IE, where IE is given by 1 equal to 1 plus beta times IB. This is equal to 51 into 44.77 microamperes. This value equal to 2.28 milliamperes. Substitute this IE value in the RE, where RE is the emitter resistance. It is given by RE equal to 26 into 10 to the power of minus 3 divided by 2.28 into 10 to the power of minus 3. This value equal to approximately 11.4 ohms. This data RE values varies as the R1, R2, RC and RE values are also varies. Therefore, this is less accurate. Next, we have to find the given data, that input impedance, output impedance and a voltage gain. Input impedance is given by ZB is equal to beta times RE. This is equal to 50 into 11.4. This value equal to 570 ohms. Then this is when you are looking into ZB is the, when you are looking into this. I want to determine that input impedance ZI. For the ZI, where ZI is given by a parallel combination of ZB is in parallel with R1 is in parallel with R2. This is also equal to ZB is in parallel with RB. This is equal to 570 into 9091 divided by 9091 plus 570 ohms. This input impedance value equal to 536.4 ohms. Because of this biasing resistances, its input impedance is slightly less than the transistor impedance. After finding this ZI, next step is to find a Z0, output impedance. Output impedance of a transistor is given by, we are looking into the, because your output is to be taken across this point, we are looking into this point. When you are looking into this point Z0, where we know that already R0 is 0, then Z0 is approximately equal to RC. This is equal to about 5 kilo ohms. Once we find the output impedance, next is we need to calculate a voltage gain. Voltage gain AV is given by V0 by Vi. Either you have to applying KVL or analyze. Already we know that the formula, this is nothing but minus RC by RE, where RC is 5 into 10 to the power of 3 and RE is 11.4 ohms. Then this ratio is equal to minus 439. This negative sign is indicating that a phase reversal between the input voltage and a output voltage. A current gain I is given by beta times RB divided by RB plus ZB. This is equal to beta is 50, RB is 9.09 into 10 to the power of 3. This is 9091 plus 570 ohms. This value is approximately equal to 47.05. Means if that in numericals, either you have to analyze by writing an equivalent circuit and then analyze, or you can remember few equations and then you have to calculate the values of that input impedance, output impedance, a current voltage gain and a current gain. This is one of the example for the a voltage divider emitter bias circuit. Next example is determine ZI, Z0, AV and AI for the circuit shown in figure. A given data, beta is 45, VCC 20 volts, RC 5 kilo ohms and RF 100 kilo ohms. For this circuit, earlier we are not analyzed, means whenever that any circuits are given, next step is first step is you have to determine that or derive an expression for the corresponding values, and then you have to substitute to find the respective values by given data. For this value, this the circuit given is, this is your VCC, and then this is your transistor, and then here that resistance RF is connecting between a collector and a base, and emitter is grounded. Output is to be taken across ground and this point, and then input is applied between that base and a emitter circuit. When this circuit is given, the current flowing through this is nothing but IC plus IB, and then current flowing through this is IC, current flowing through this is IB, current flowing through this is IE. For this circuit, we need to analyze, because earlier we are not analyzed this circuit. For this circuit, to determining an analysis means you have to replace this transistor with its equivalent circuit. For this transistor with its equivalent circuit means you have to write this is beta times RE, and then here that current flowing through this is nothing but beta times IB, where this is your collector, emitter, base and a emitter. The current flowing through this is IB, current flowing through this is IC, across collector current. After transferring this equivalent circuit, next step is you have to transfer that equivalent circuit resistance values RC and RF into this equivalent circuit. For this equivalent circuit, you have to set that VCC is equal to 0. When VCC is grounded, this terminal is connecting to the ground, where this point that resistance RC lies in between the collector and a emitter. Resistance RC is collector between the emitter. That current flowing through this is in the direction of that a collector towards the collector. That current is to be IC plus IB. Output is to be taken across this point. Then this resistance RF, when this is set ground, that RF is lies in between a base and a collector. Means there is a resistance in between this resistance, where this current is to be IB, and then in the DC analysis, this current flowing through this is something called I dash. This input is applied, this input is applied, VI current due to the voltage applied is VI. For this, you have to analyzing this circuit to determine the input impedance, output impedance, a voltage gain and a current gain. We know that already. First, you have to determine the input impedance. For the input impedance, already we know that by definition that Zi is equal to Vi by Ii. For this circuit, what is Ii? Ii is nothing but at this node, current flowing at this node, Ii is equal to sum of that current IB plus I dash, where IB is the current flowing through the resistance beta times RE, where I dash is the current flowing through the resistance RF. You need to determine I dash. To determining an I dash, that is given by I dash is the current flowing through that, you have to finding the potential difference across this voltage at this point is Vi, voltage at this point is V0, hence this is nothing but V0 minus Vi by RF. Then what is V0? V0 is nothing but, and V0 is nothing but IC, the current flowing through this is nothing but IC plus IB times RC. This is equal to this current IC is nothing but sum of these two. This is beta times IB plus I dash into RC. When this I dash is to be very small, negligibly small, then this is nothing but beta times IB times RC minus, because this current, this is plus, this is minus, minus beta times IB into RC. For this circuit, and then that IB is equal to, and IB is nothing but a current flowing through that beta times RE, voltage up across this resistance is nothing but Vi, hence that IB is equal to Vi divided by beta times RE. Hence, you are going to get Vi is equal to IB into beta times RE. You have to substituting this V0 and Vi into this equation I dash, then I dash is given by is equal to V0 is minus beta times IB RC. This is minus IB beta times RE divided by RF. For this calculations, we need to find this value where IB is nothing but from this circuit. IB is nothing but where IB is VI by beta times RE. If you substitute, keep this is VI. If you substitute from this equation, this IB is equal to minus beta RC by RF into VI by beta times RE minus VI by RF. This beta cancels. Then I dash is nothing but VI into VI by RF into this is RC by RE plus 1. Once you need to find this I dash, now we have to calculate the input impedance Zi, where Zi is nothing but on Vi by Ii, where Ii is nothing but this equation. Therefore, Zi is equal to Vi divided by, where Ii is equal to Ib plus this. Then you are going to get this value as this is nothing but Zi is equal to, sorry, Ii is equal to Ib. This where I dash is nothing but minus Vi by Rf into Rc by Re plus 1. These are correct. Then that applying KVL to this circuit, then Vi is equal to Ib times beta Re. Vi is equal to that voltage across the total current is given by this. Then this is given by Vi is equal to Ib times beta Re. This is equal to Vi is equal to Ib beta times Re, where Ib from this equation, this is nothing but Ii minus I dash into beta Re. This is equal to where Ii beta Re, where I dash is given by this expression, minus into minus, this will becomes plus. This is equal to Vi divided by Rf into Rc plus Re plus 1 into beta Re. You have to solve for that Vi, then you are going to get this is equal to Zi is approximately equal to Vi by Ii. This value, if you are simplifying this equation, you are going to get this value equal to beta times Re divided by 1 plus beta Re by Rf plus into 1 plus Rc by Re. Means you have to substituting this Zi is given by this expression. The input impedance of this circuit or a feedback collector base feedback circuit is given by beta Re divided by 1 plus beta times Re by Rf into 1 plus Rc by Re. Next, you need to determine the output impedance. Later, we calculate all the values. First, you have to calculate the output impedance. Output impedance is nothing but when you are looking into this resistance Rc. We are finding an output impedance Z0, you have to set Vi is equal to 0. When Vi is equal to 0, that current Ia is equal to 0, this is acting as a open circuit. Means when Vi is equal to 0, this beta times Re is acting as a short circuit. Then its equivalent circuit is Rf, and then this resistance, because this beta times Ib is acting as a open circuit, then this is equal to Rc is like this. This is Z0, where Z0 is nothing but a parallel combination of Rc and Rf. This is equal to Z0, simply you are going to get this is Rc is in parallel with Rf. I am calling this another equation 1, you can call 2. Next, you have to determine a voltage gain. That voltage gain AV is equal to V naught by Vi, where V naught is nothing but, already from this analysis we know that V naught is equal to minus IB beta times IB plus I dash into RC, where I dash is very small when compared to that beta times IB. Therefore, V naught is approximately equal to minus beta times IB RC. Next, Vi is given by that already from this expression, that is IB times beta times IB into beta times RE. Hence, that voltage gain AB is equal to, if you take this ratio, you are going to get minus RC by RE. This output impedance is a voltage gain of a collector feedback circuit is independent of this feedback resistance RF. Next, we need to calculate the current gain. Current gain of this is given by that AI is equal to I naught by II, where what is I naught? I naught is nothing but IC beta times IB plus I dash. This is equal to I naught is equal to beta times IB plus I dash, and II is given by that current IB plus IB plus this. Now, you have to determine that a current gain, you have to finding this ratio I naught by I, applying a feedback loop to from this output circuit, you are going to get this is equal to V naught minus the voltage drop across the feedback resistance RF and plus Vi is equal to 0. You have to solve what is the voltage drop across VRF. That VRF is nothing but a potential, this is nothing but V naught, that current flowing through this voltage drop across the I dash into RF. This is given by V naught minus Vi divided by I dash. Then this is equal to Vi is equal to IB beta times RE minus V naught is nothing but beta times IB RC, and a voltage drop across this RF is given by this current flowing through this is nothing but minus I dash into RF is equal to 0, where I dash is nothing but a difference between this from this equation already we know that II is equal to IB plus I dash, then I dash from this equation I dash is equal to II minus IB. This is, if you substituting this, you are going to get this value IB into beta times RE minus beta times IB RC. I dash is nothing but minus of II minus IB into RF equal to 0. If you are simplifying this equation, you are going to get that a current gain AI is given by if you are simplifying this equation and also substituting this I naught is equal to beta times IB, then you are going to get that I naught by II is given by that expression beta RF divided by RF plus beta RC, exact expression for the current gain. If you want approximate, if this beta times RC is much greater than RF, then AI is approximately equal to RF by RC. This is equation 4 and then this is equation 5. Means here in this example these expressions are not readily available, then you need to determine or derive an expression for the input impedance, output impedance, voltage gain and a current gain. Later you have to substituting these values and then you can going to get the a current gain, voltage gain and input impedance, where that input impedance Zi is equal to, from the equation 1 already we know that this is equal to beta times Re divided by 1 plus beta times Re by Rc into plus Rf. This value, if you are substituting into this expression, so we are substituting that Re, Rc, Rf, we need here once again this Re value is unknown. To determining an Re value, you have to determine, you have to analyze perform the DC analysis. To determining an Re value, you have to perform the DC analysis, where in the DC analysis already we know that Re is equal to 26 into 10 to the power of minus 3 by I. To performing the DC analysis is applying a KVL to the input circuit. Then applying KVL to the input circuit, you are going to get this is equal to VCC minus RC into IC plus IB minus RF into IB minus VBE equal to 0. You have to solve for this current, then this IB into, where IC is equal to beta plus IB, therefore you can write IB into 1 plus beta times RC plus RF equal to VCC minus VBE. You are going to get this value IB is equal to that 20 minus, given data is 20 minus 0.7 silicon transistor and divided by, this is equal to 1 plus beta is 46 into resistance is given as 5 into 10 to the power of 3 and RF is 100 into 10 to the power of 3. Substitute and then simplifying this expression, you are going to get the value of that current IB is equal to 58.48 microamperes. After getting this IB value, you need to determine IE value, where IE is equal to 1 plus beta times IB, where that IB is given, substituting this expression, you are going to get 46 into 58.48 microamperes. This value results in 2.69 milliamperes. Then you are substituting this IE value, RE is equal to 26 into 10 to the power of minus 3 divided by 2.69 into 10 to the power of minus 3. This value equal to approximately 9.66 ohms. After finding this RE value, you are substituting this RE value into the derived expression, then you are going to get a input impedance Zi is given by an expression approximately equal to beta times Re divided by 1 plus beta times Rc by Rf is given by 1 plus beta times Rc by Rf. If you are substituting this value, you are going to get beta is 45 into Re is 9.66 divided by 1 plus 45 into Rc is 5 into 10 to the power of 3. This Rf is about 100 into 10 to the power of 3. This value equal to approximately 133.75 ohms. You can, input impedance of this circuit is given by approximately equal to, round off to the round figure, this is equal to 134 ohms for this circuit. And then output impedance is given by Z0 is, next is output impedance is nothing but Rc is in parallel with Rf. Rc is 5 into 10 to the power of 3 is in parallel with, this is Rc Rf divided by Rc plus Rf. This value equal to 5. This resistance value is 5 plus 100 divided by, into 100, 5 plus 100 into 10 to the power of 3. This value is less than 5 kilo ohms. This value is approximately equal to 4.5 0.76 kilo ohms. Next is a voltage gain AV. Voltage gain AV is given by V naught by Vi. This is equal to minus RC by RE, where minus 5000 divided by RE value is 9.66 ohms. This ratio, if you calculate this, approximately equal to this gain is to be approximately 500. If you use exact value, this value is equal to 517.6 minus. And current gain, a current gain AI is given by beta times RF divided by 1 plus RF plus beta times RC, where beta is 45 into RF is 100 into 10 to the power of 3 divided by 100 into 10 to the power of 3 plus 45 into 5 into 10 to the power of 3. This value results in approximately 13.85. Means whenever the circuits are given like this, if it means already we studied earlier the voltage divider and a fixed bias circuit. For any circuit is given, we need to replace the circuits with equivalent analysis, equivalent circuit and analyze, and then you have to determine the corresponding parameters. This completes the an RE model. For some more examples, you have to refer the textbook Electronics Devices by Ballisted. Next, the another alternate modeling is an hybrid parameters. This RE model is based on the diode equivalent circuit. The hybrid model of any linear network is depends on the transistor parameters. If you consider this is the block diagram of any network, a linear network, we have a two input terminals that denoted as 1 1 dash. Current flowing through this is I1, current voltage applied across this is V1. The network is that output terminal is taken across 2 dash, current is driven by this is I2, voltage up across this is V2. This is an introduction to the hybrid parameters. Then how do you link these I1 V1 and I2 V2? Because in the circuit analysis already we know that there are 4 kinds, and then out of this we are going to use an hybrid parameters. How do you link these two? Where this empty box is replaced with its equivalent model. For this equivalent model, inside this box there is a terminal 1, there is an 1 dash, current flowing through this is I1, the voltage up across this is V1. Then this is given by an equivalent circuit is this is H11, and then there is a constant voltage source, this is given by H12 into V2. And the output side, this circuit is driven by, that output current is to be driven by a voltage I2 is driven by V2, this is applied voltage, this is plus minus, and then this is to be replaced with a constant a current source, this is H21 I1, there is a conductance that is H22. Okay, this means whenever there is a empty box, any linear network can be replaced with its equivalent hybrid parameters, that is in terms of H11, H12, H21 and H22. Now we need to define that what is H11, what is H12, what is H21 and what is H22. For this, if you are applying this, if you observe, this is output circuit is driven by constant current source and input circuit is driven by an voltage source. Therefore, you have to apply a KVL to the input circuit and apply a KCL to the output circuit. From this circuit, you are going to get this V1 is equal to that I1 H11 plus V2 H12, or we can also write in the other way, Vy is equal to V1 is equal to H11 I1 plus H12 V2, and applying KCL to this node, then this I2 is given by, from this circuit I2 is given by applying KCL means that is H21 I1 plus H22 into, because this is a conductance S22, then you have to find this voltage of current flowing through this is nothing but S22 into V2. This equation is 1, this equation is 2. To determine this H11, H12, S21, S22 in terms of Vi, I1, V1, I1, V2, I2. For this circuit, we have to analyzing this circuit. When do you get this H11? Where H11 is defined as that V1 by I1 when this V2 is equal to 0. If you set V2 is equal to 0 means if this is a 0, it is a short circuited, means this is open circuit, means that current means when this is 0, then this current source is acting, a constant voltage source is acting as a short circuit, then applied voltage V1 is equal to I1 into H11, hence we are defining that H11 is equal to V1 by I1, where this is nothing but the ratio of this H1 by I1 is nothing but a input impedance, because you are looking into the input terminals of a 2-port network, therefore it is known as a input impedance, but here V2 is 0, therefore it is known as a short circuited input impedance. Its value is given by in terms of, measured in terms of a ohms. And similarly, to determining an H12, this current should be 0. When current 0 means that voltage up across this point is 0, then you are going to get V1 is equal to V2 H22, sorry H12, this when I1 is equal to 0. This implies that H12 is equal to V1 by V2 with I1 is equal to 0. When I1 is equal to 0 means it is acting as a open circuit. Therefore, this is a ratio of, that is a voltages, that is a V1 by V2. Already we know that a V2 by V1 is defined as a current voltage gain, but it is a ratio of, that is a V1 by V2. Hence, it is known as a open circuited reverse voltage gain. Reverse voltage means that input is to be driven by that output voltage V2. Therefore, hence it is known as H12 is to be defined as a open circuited a reverse voltage gain. And similarly, at applying the same conditions here, when this V2 is equal to 0, then you are going to get H21 is equal to I2 by I1 with V2 is equal to 0. When this V2 is equal to 0 means this voltage up across this is acting as a 0 open circuit, because it is a conductance is acting as a open circuit, hence this I2 is equal to simply S21 into I1. This V2 is equal to 0 means it is known as a short circuited, where the ratio of that output current to the input current is nothing a current gain, but therefore it is known as, it is a means that current I2 is to be driven by this an input current I1, therefore it is known as a forward current gain. These two, that H12 and H21 are the ratios of that V1 and V1 by V2 and I2 by I1 respectively. These two are dimensionless. Next, to determining that H22 is equal to, that is I2 by V2 with I1 is equal to 0. When I1 is equal to 0, this ratio of that, by according to Ohm's law, I by V is nothing but a conductance, where I2 and V2 are the, I2 is the current flowing at the output terminals and V2 is the voltage measured across the terminal 2 dash. Hence, it is known as I1 is 0 means it is known as an open circuited. This ratio according to Ohm's law, that I by V is nothing but a conductance, hence it is known as a open circuited output conductance of a network. Its units are either a mhos or it is also known as a Siemens. This the unit of that H11 is ohms, V1 and V2 are dimensionless, and S22 are measured in terms of mhos or a Siemens. Hence, these two, these dimensions or the units are different, hence this network analysis is known as an hybrid network analysis. After defining this, what do you mean by this H11, H12, H21 and H122? For this H11 is defined as that input impedance we are looking into, therefore, it is denoted with a suffix Hi, and H12 it is defined as a open circuited reverse voltage gain, hence it is known as denoted with HR suffix, and H21 is defined as a short circuited forward current gain, hence it is denoted with an HF, and H22 is a open circuited output conductance, that is denoted with a suffix H0. Then this circuit, this two port network is written equivalently instead of an H11, H12, H11, then this can be defined as Hi, HR into V2, this is HF into I1 and conductance H0. The terminals are 2, 2 dash, this current flowing through this is I2, this current is plus minus, this voltage at this point is V1 and current flowing through this is I1. Means instead of using this a general H11, H12, H21, H22, it is replaced with its input impedance, output impedance and a reverse voltage gain and a forward current gain. This is a general two port network. How do you apply for this a transistor? Next question arises. For a transistor circuit, if you consider a common emitter amplifier. Okay. In the next class, here we are to defining a general circuit diagram. In the next class, we are going to, in this, this is to be given by this. Next, we have to consider the equivalent circuit of a transistor. If you consider a simple common emitter amplifier, we know that already voltage of this function is to be given by VBE, and this is your base, and then this is your collector emitter, and then current flowing through this input current is IB. Output is to be taken across a collector and emitter, and then this is denoted with VCE, and current flowing through this is output current is given by IC. Then how these input current, output current, input voltage and output voltages are related. For this case, you have defined already, we know that from these transfer characteristics that a input voltage VBE is some function of F1, a function of IB and VCE, and similarly that output current IC is given by some other function of that IB VCE. Then how do you obtain this relation? Can you guess? Means because these two VB and VIC are two functions of that same values IB and VC. Then what is the relationship between this? This can be obtained by taking that applying on Taylor's expansion. By Taylor's expansion, you are defining this VBE is given by means a change in a voltage VBE, because you have to a partial derivative of this is given by delta F1 with respect to delta partial derivative of IB with VCE constant into delta IB plus delta F1 divided by delta VCE with IB constant, and similarly delta IC is given by delta F2 by delta IC with VCE constant into delta IC, in the similar delta F2 divided by delta VCE with constant IB, constant into delta IB. In the earlier case, when you are defining that H11, H12, H1, S21 and H0, you are defining that H0, VCE 0, IB 0, I1 0 and V2 0. But here in a transistor, this circuit is to be biased with a DC current, then the current flowing through this is to be transistor is given by IB is the total instantaneous current. This is nothing but IB plus IB. For a change in for an incremental current and a voltage, this IB 0 means this you have to defining with respect to the constant, a DC current that is given by IB is constant. Instead of 0, you are considering that a DC voltage and DC currents VC 0 and IB 0. From this analysis, you are going to determine that ratio of this delta F1 by delta IB is nothing but an input HI. This is nothing but, this value is nothing but HR. This is the ratio, this is nothing but HF, and this value is nothing but H0. In the next class, we are going to determine that relationship between that this using this relation, and then you have to define a equivalent circuit for this transistor, and then you have to link with respect to the constant value. Today we are summarizing this class or session with a examples on RE model, and then you have to defining that a transistor hybrid parameters that HI, HR, HF and I2. Thank you.